When you see water boiling, a candle burning, or iron rusting, you're witnessing the properties of matter in action. In chemistry, observing isn't enough, we must measure, quantify, and record. This leads us to one of the most important foundations in chemistry, understanding the physical and chemical properties of matter and learning how to measure them accurately. Let's begin with a simple question: how do we describe a substance? We do that by looking at its properties, and they come in two types: physical properties. These are things you can observe without changing what the substance is. Think of color, melting point, boiling point, or density. For example, melting ice, it's still water, just in a different form. Chemical properties. These reveal themselves only when the substance undergoes a chemical change. Like how something reacts with acid, whether it's flammable, or how it oxidizes over time. Take burning wood, for instance, it turns into something entirely new. That's chemistry in action. If the change alters the identity of the substance, it's chemical. If it doesn't, it's physical. Let's keep that distinction in mind as we move forward. To truly understand and compare substances, we need more than just observation, we need to measure their physical properties. And here's something important: every measurement has two key parts: a number, which tells us the magnitude, and a unit, which gives that number meaning. For example, 5 meters, the number 5 is the magnitude, and meters is the unit that tells us what we are measuring. This combination is what makes science quantitative, precise, accurate, and universal. Because in chemistry, a little more or a bit less isn't good enough, we deal in exact values backed by measurements. In science, precision matters. And to ensure that scientists across the globe speak the same measurement language, we rely on the SI system, that's Système International d'Unités. This system gives us 7 base units used universally in chemistry and other sciences. Let's take a look: length measured in meters, mass kilograms, time seconds, electric current amperes, temperature Kelvin, amount of substance moles, luminous intensity candelas. These are the building blocks of all measurements. From here, we derive other units like volume, speed, and density, all built on the foundation of these 7 C units. Here's a common mix-up in science: mass and weight are not the same thing. Let's break it down. Mass is the amount of matter in an object. It's constant whether you're on Earth, the Moon, or floating in space. Its SI unit, kilogram, kg. Weight, on the other hand, is a force, the pull of gravity on that mass. And because gravity varies by location, weight can change. The same object weighs less on the Moon than on Earth. We calculate it using the formula: weight is equal to mass times gravitational acceleration, and the C unit of weight, that's the Newton, N. So remember, mass stays the same, but weight depends on where you are. Let's talk about volume. It's simply the space that matter occupies. The C unit of volume is the cubic meter, or m cube. But in the chemistry lab, we use some more convenient equivalents. 1 liter is 1000 milliliters, or 1000 cubic centimeters, or 1 decimeter cubed. And 1 cubic meter is 1000 liters. To measure volume precisely, we use lab tools like measuring cylinders, burettes, pipettes, volumetric flasks. Whether it's a drop of acid or a beaker of solution, volume tells us how much space it takes up. Let's explore density, a property that tells us how tightly packed the particles are in a substance. It's defined by a simple formula: density equals to mass divided by volume. The C unit of density is kilogram per cubic meter, but in chemistry labs, we often use grams per cubic centimeter or grams per milliliter. They're more practical for smaller samples. Here's a quick way to think about it. The more mass in less space, the higher the density. Example, a block of lead feels heavy and compact, whereas a bag of cotton is light and fluffy, even if it's bigger. That's because lead is denser than cotton. So, density helps us understand not just what something is, but how its particles are arranged inside. Let's now understand temperature. It tells us how much thermal energy a substance has. There are three main temperature scales we use: Celsius, freezing point, 0 degrees Celsius; boiling point, 100 degrees Celsius; Fahrenheit, freezing point, 32 degrees Fahrenheit; boiling point, 212 degrees Fahrenheit; Kelvin, freezing point, 273.15 Kelvin; boiling point, 373.15 Kelvin. Kelvin is the C unit of temperature used in science. To convert Celsius to Kelvin, just use K equals to degrees Celsius plus 273.15. And here's a fascinating fact: Kelvin never goes negative. That's because it starts at absolute zero, the point where all molecular motion stops. In chemistry, temperature isn't just about hot or cold. It's a measure of energy at the atomic level. So, what have we uncovered so far? Matter has both physical and chemical properties. To study it, we need precise and reliable measurements. The C system ensures global consistency in how we measure. And mastering the basics, mass, volume, density, and temperature, forms the foundation for everything else in chemistry. Ready to level up? In our next video, we'll explore how to work with very large or tiny numbers using scientific notation, and how to deal with uncertainty in measurements, because even in science, there's room for approximation.